If this steel box suddenly began accelerating downward, the computer could lose power, the motor could stop responding, and the main brake could fail to hold it. Yet hidden inside the shaft is another system that does not need cameras, artificial intelligence, or even a working power supply. It measures speed using centrifugal force, then uses the dangerous motion of the elevator itself to clamp the car onto two steel rails. But stopping several tons of moving machinery creates another problem. The system must react quickly without bringing the passengers to a violently abrupt stop. Movies often show an elevator hanging from a single cable. The cable snaps, and the car immediately enters free fall. A modern traction elevator is built very differently. The car is normally supported by multiple steel ropes or reinforced traction belts operating in parallel. Each steel rope contains many smaller wires twisted into strands, creating redundancy and a large safety margin. These suspension ropes pass over a traction sheave and connect the elevator car to a counterweight. The counterweight balances the car and part of its normal passenger load, reducing the force required from the motor. Instead of lifting the entire mass directly, the traction machine mainly controls the difference between the two sides. The simultaneous failure of every suspension rope is therefore extremely unlikely. A more realistic danger is uncontrolled speed. A drive fault, braking problem, or abnormal mechanical condition could allow the car to move faster than its design limit. Detecting that acceleration requires a device that remains independent from the motor control system. Near the top of the hoistway is a mechanical device called the centrifugal overspeed governor. A separate steel governor rope passes around its upper sheave, travels down the shaft, loops around a tensioning pulley near the bottom, and returns upward. This rope does not support the elevator. It moves with the car and continuously reproduces its speed. While the elevator travels normally, the governor sheave rotates at a predictable rate. Inside it, centrifugal flyweights are held inward by calibrated springs. As rotational speed increases, centrifugal force pushes the weights farther away from the center. Their movement is small, but it provides a direct mechanical measurement of elevator speed. Normal acceleration does not activate the system. The springs and trip mechanism are calibrated so the flyweights must reach a specific position before anything happens. When the car exceeds the permitted speed, the moving weights contact the governor trip latch. The first response is usually electrical. An overspeed safety switch opens the elevator safety circuit, removing power from the traction machine and allowing its spring-applied brake to close. In many faults, this action is enough to stop the elevator, but the governor does not assume that the machine brake will succeed. If the car continues accelerating, the mechanical trip advances to its next stage. The governor grips and stops the governor rope. Locking. This relatively small rope cannot directly stop a car weighing several tons. Instead, it begins a carefully designed chain reaction underneath the elevator. The governor rope is connected to a mechanical safety linkage on the elevator car frame. When the rope stops but the car continues moving downward, relative movement develops between them. That movement pulls an operating lever connected to a transverse shaft beneath the car. The shaft rotates and moves pull rods toward both sides of the frame. These rods raise the safety gear wedges positioned beside the guide rails. Under normal operation, the wedges remain retracted with a narrow clearance, allowing the car to travel without contact. As the linkage lifts them, their angled surfaces force them inward against the steel rails. The farther the car attempts to move downward, the deeper the wedges are drawn into the safety gear, and the greater the clamping force becomes. The elevator therefore supplies the energy needed to activate its own brake. Downward movement pulls the linkage. The linkage drives the wedges. The wedges convert vertical motion into an increasing sideways force against the rails. However, locking the car instantly would expose its structure and passengers to an extreme deceleration. High-speed elevators therefore use progressive safety gear designed to build braking force in a controlled way. As the wedges contact the rails, calibrated springs, friction surfaces, and energy-absorbing components allow the clamping force to rise gradually. The car continues moving for a short, controlled distance while kinetic energy is converted into heat at the braking surfaces. The safety gear on both sides must engage almost simultaneously, If only one side applied full force, the elevator frame could twist inside the hoistway. A mechanical cross-shaft synchronizes the left and right mechanisms, so both guide rails share the braking load. Those rails normally keep the car aligned as it travels between floors. During an overspeed event, they take on a second role. Their machined steel surfaces become two continuous braking tracks extending through the shaft. Once the car has stopped, the wedges remain mechanically locked against the rails. They do not need electrical power to keep holding the elevator. Technicians must secure the system, remove the load from the safety gear, inspect the installation, and manually reset it before the elevator can operate again. There is still another protective component at the bottom of the hoistway. Hydraulic or spring buffers are positioned beneath the elevator car and counterweight. But these buffers are not intended to catch a car falling uncontrolled from the top of the building. Their purpose is to absorb energy if the elevator travels beyond its lowest normal stopping position at a limited speed. They are the final protection against overtravel near the bottom, after the control system, machine brake, overspeed governor, and rail-mounted safety gear have already provided earlier layers of defense. The entire safety sequence is built so that one failure does not automatically become a catastrophe. The controller monitors normal movement. The machine brake closes when power is removed. The governor independently measures actual speed. The governor rope activates a mechanical linkage. Progressive safety gears clamp the car to the guide rails. Pit buffers protect the end of the remaining travel. The most remarkable part is that the final chain requires no complex decision. The car moves too fast. Centrifugal force releases a latch. The governor rope stops. Relative motion pulls the linkage. The wedges enter the rails, and the force driving the elevator downward becomes the force that stops it. For years, this mechanism may rotate quietly without ever being triggered. But when every earlier layer fails, a system made from ropes, springs, levers, wedges, and steel rails is ready to turn the elevator shaft itself into one enormous emergency brake.